Hi guys, so here's a energy transfers video lecture which most of you requested, and I hope this is helpful. So here's the situation. We have Matt, who's nervous about jumping off a diving board for the first time. Here's Matt peering over. We can assume the water level is below. This is the bumpy water. The platform is 22 feet above the surface of the pool, so we could set the pool level as height equals 0, and Matt weighs 72 pounds. That's all we know, and we should be able to answer several questions based on this scenario. So for part A, we are labeling any given information and any type of energy that might be present. So we know that he has a mass of 72 pounds. So I'm going to go ahead and label this by Jimmy. Mass equals 72 lbs is the abbreviation for pounds. And then I'm also going to list that the platform, I'll list it over here, height equals, let's leave this lowercase, equals 22 feet. And let's label height equals 0 where the water is. Okay, so we have our given information labeled, and now we're going to look at what types of energy. So Matt's above ground, so we know that he has stored energy based on his height above Earth. So this could be the surface of the water, this could be something jumping on the ground, he could be midair, he could be on a roof. He has some stored energy, and it doesn't specify that he's moving, so he's not going to have kinetic energy yet. He's going to have some thermal energy because there's molecules moving around giving his body some heat. He's above absolute 0, which is colder than negative 400 degrees Fahrenheit. So I'm going to label GPE here, gravitational potential energy, stored energy based on his height above the water. Okay. And then will that energy change? So as Matt falls from or jumps from height equals 22 feet to 0, GPE is dependent on height. So as he gets closer to the water, GPE will decrease. So I'm going to copy this. And I'm going to make this smaller so it's obvious that GPE is decreasing. Okay. And then as he falls, kinetic energy is going to increase because his speed is going to increase. So anything that falls down to Earth is going to accelerate, which means it's increasing speed every second. So after 1 second, it might be traveling 10 meters per second. After the next second, it will cover 20 meters in 1 second. So we know speed is going to increase. So I will label that now. Kinetic energy, I'll label this green. And at the top, if he's not moving, let's just say kinetic energy equals 0 at the top. And let's say 0 joules, the unit of energy. Okay. And let's say this is kinetic energy max. Okay. How would we find Matt's total energy? So total energy is kinetic energy plus GPE, and will that energy change? So in any system, total energy is always conserved. Sometimes it's transferred into thermal energy or into sound, which is also called acoustic energy. And we call that waste energy because you can't really get that energy back. It's not in a useful form. So in this scenario, let's assume there's no friction in the air. There's no air resistance, so there's not going to be any waste energy. So this is an ideal scenario, which is not realistic. How would we find Matt's total energy? So we would need total energy equals KE plus GPE. So at the top, before Matt jumps, we're going to add GPE plus kinetic energy. But if kinetic energy is 0 joules, then our total energy would just be equal to the GPE at the top. So I'm going to rewrite this as total energy equals our GPE initial. And that stays constant. Okay, let's move on. Okay, so you notice that we don't have SI units, so we can't do any calculations until we stop, drop, and convert. So we need to convert mass to our SI units and height to SI units before we move on. So the height was 22 feet. We're going to put that in the numerator. Leave the denominator blank, or you could just put 1 without any units. That would be an equivalent quantity. We're trying to get rid of feet, so we're going to list feet on the denominator so that they cancel. And let's strike through this. Show that they're canceling. And our SI unit of height is meters. So let's just mass okay. And in 1 meter, there are 3.3 feet. Okay, so in your calculator, you would write 22, or type in 22 divided by 3.3, and that is 6.67 meters. So this is the value we'll use for height when we plug into the equation. And then his mass, let's double check, was 72 pounds. So 72 lbs. We're getting rid of pounds. We're converting to kilograms. And there are 2.2 pounds in 1 kilogram. And let's strike through this. And strike through this. And then we are going to type in what the calculator is, 72 divided by 2.2. 72 divided by 2.2, 32.73 kilograms. Okay, so these are the values we'll move forward with in our scenario. So the next kind of step is calculate Matt's GPE on the diving board before he jumps. So to calculate GPE, we need GPE equals mass times gravity times height. So we know the mass is 32.73 kilograms. We just converted that. Leave this as a lowercase m. We know gravity is constant on Earth, 9.8 meters per second squared. And we know the initial height is, let's look back, 6.67 meters. Okay, so if I plug into the equation for GPE, I'm multiplying all these values together. So I would multiply 32.73 times 9.8 times 6.67. And I get 2,139.43 joules of stored energy before he jumps. And this is also equal to the total energy, which we listed in the previous slide, equals GPE initial. Okay, what is Matt's stored energy at 11 feet above the pool? So this is basically just asking how would the GPE change if Matt is now halfway to the pool. So you don't necessarily need to convert 11 feet into meters. We know that 11 is half of 22. So if GPE is divided by 2, we know that mass isn't changing over here in the equation. Gravity isn't changing. We do know that height is divided by 2. So GPE is going to be divided by 2. And so let's plug in 2,139.43 divided by 2. Equals 1069.72 joules. Okay, so this is the GPE at about this point if we say this is halfway down, and then right as he hits the water, because height is 0, we're essentially plugging in 0 to this mass times gravity times height equation. Anything times 0 would give us 0. So we have 0 joules of GPE if you know the height is 0. No stored energy because there's no height. So this confirms that our gravitational potential energy of Matt is decreasing. So let's keep going. What is Matt's kinetic energy at the top before he jumps? So at the very top, if he's not moving, there's no velocity. So there is no kinetic energy. And let's rewrite our kinetic energy equation. 1/2 mass times velocity squared. What is Matt's kinetic energy halfway to the bottom? So for this question, we can apply a previous answer. So we know that the total energy has to equal KE plus GPE. And we know that the total energy was equal to the initial GPE. So the initial GPE was this value. Copy and paste this over. Okay, equals, we're trying to solve for the kinetic energy halfway down. I'm just going to add a subscript halfway. Okay, and we don't know kinetic energy halfway yet, but we do know the GPE halfway down, which was this value. Okay, so if we rearrange this equation, we can find that kinetic energy halfway down for Matt is equal to 2139.43 minus 1069.72, which is equal to 1069.71 joules. So because we rounded these two values, we're not going to get a number that's exactly divided in half. If we had a number like 10 for total energy at the top, we would have 5 joules of GPE and 5 joules of kinetic energy at the halfway point. So it's essentially splitting, and this confirms our conceptual analysis, which says that kinetic energy is going to increase because speed is increasing. Okay, so we have this value now. Okay, what is Matt's kinetic energy right before he hits the water? So we could plug this into the equation again, and instead of the halfway value for GPE, we could plug in 0 joules, or we could just use our energy transfer conceptual analysis and say that all of the GPE from that at the top, all the stored energy, converts into kinetic energy right before he hits the water. So the final kinetic energy should be equal to the initial stored energy at the top, and that's equal to the total energy. So 2139.43 joules should be the kinetic energy of Matt right before he hits the water. Okay, and then now we're looking at his final velocity right before he hits the water. So we know the kinetic energy final equals 2139.43 from the answer to question C. We also know that his mass is 32.73 kilograms, and we are looking for his final velocity. So the equation for velocity is that square root of, can't find the symbol right now, square root of 2 times the kinetic energy over mass. And you have to take the square root of the entire fraction. So I need to multiply 2 times 2139.43 divided by 32.73. And that gives me the square root of 130.73, and that equals so if you have a smartphone, if you unlock the portrait orientation and you rotate your calculator, you should be able to find the square root button. And I get 11.43 meters per second. And I know I'm going to end up with the SI units of velocity because I started with SI units of mass and SI units of kinetic energy, which are joules. Okay, so we can highlight this number as well. Okay, so to calculate the final velocity of an object, all you really need to know is the GPE, the mass, the height, the gravity at the top, if you assume that all energy is being transferred to kinetic energy in the absence of friction, absence of air resistance. I hope this was helpful in analyzing energy transfers and what happens to total energy. It's kind of a puzzle to piece together, and conversions, as always, are part of it. Please comment below with any questions, whether it was the calculation or the concepts, and I hope this was helpful. See ya.